Senior Physics Lab Ionizing Radiation Safety Induction. In the Senior Lab there are many experiments that use ionizing radiation. You'll recognize them with this well-known symbol. Although we take all measures to ensure that the experiments are safe, it's important you also do the same while doing the experiments. No matter how weak the radiation source, you should always aim to minimize your radiation exposure by keeping your exposure as low as reasonably achievable. This is the so-called ALARA principle and can be achieved in three ways. Minimize your exposure time, maximize your distance from the source, use shielding. However, we have done the shielding whenever possible. We'll shortly look at examples on how you can minimize your exposure time and maximize your distance. But first, here is how we quantify radioactivity. The unit of radioactivity is the becquerel. 1 becquerel is 1 nuclear decay per second. An alternative unit is the curie, where 1 curie equals 3.7 by 10 to the 10 becquerel, or 37 gigabecquerel. The products of nuclear radioactive decay are alpha, beta, gamma, and neutron radiation. For example, here is a sodium-22 1 microcurie gamma source from one of the experiments, which has a half-life of 2.6 years and was manufactured in February of 2013. So in principle you can work out its current activity. This is regarded as a low-activity radiation source, but it's still important to follow the ALARA principle, since even the lowest activity sources can be dangerous if misused. This source is housed in a lead castle on the table next to the experiment. Keep it in its lead castle until it is needed. It's best to hold it by its wooden holder and keep your fingers well away from the source. Place it in the position required for the experiment as quickly as possible, and don't stand near it if you don't need to. When you're finished with the measurement, place it back in its lead castle. In this way you minimize your exposure time and maximize your distance. Here are other examples of low-level gamma sources. They are either placed within a block of wood that naturally keeps your fingers away from the source, or mounted on it. In this case, just hold the source by the wooden support. Here are some alpha particle radiation sources. Although alpha particles are easily absorbed by a few centimeters of air, they are quite damaging if placed next to living tissue. Keep these sources in their plastic holders until needed. Hold them by their metal support. Keep your fingers well away from the source. Quickly and carefully place them where they are required for the experiment. As soon as you have finished taking measurements, place them back in their holders. This is a neutron radiation source. Although the source is only a couple of centimeters in diameter, it has a relatively high activity. For this reason it has been heavily shielded so as to minimize exposure to very low levels. In this experiment you are required to insert a metal sample at the top of the device. The sample then moves under gravity and is guided to the neutron source at the center of the shielding. The equipment required for logging data as well as analysis is about 4 meters away from the source. So only be near the source when inserting the sample and when releasing it so that it can fall and be guided to a Geiger counter below. Don't stand near the source when you don't need to. Finally, this is a cesium-137 gamma source of relatively high activity. However, it has been heavily shielded with lead, so no gammas can escape. This lever allows a very narrow and collimated beam of gammas to exit the enclosure once this lever is in the upright position. Although there is thick lead shielding all around to minimize exposure from scattered gamma particles, use the ALARA principle and keep the lever down to shut off the gamma rays if you are not doing that part of the experiment. It's virtually impossible to avoid radiation exposure in everyday life. So let us look at what are considered to be acceptable limits of radiation doses. The amount of energy from radiation is measured in units of gray. 1 gray is equal to 1 joule of radiation energy deposited in 1 kilogram of matter. However, this unit alone does not give any information about biological damage. So a related unit called the sievert enables a quantitative measure of biological dose. It's related to the gray by a factor Q, called the quality factor, and is dependent on the type of radiation. Approximate values of Q for the various radiation types are 1 for gamma and beta particles, 10 for neutrons, and 20 for alpha particles. You can see that alphas are the most damaging if their energy is deposited into biological tissue. To place these numbers in context, consider the normal background radiation dose we all experience from various sources such as the ground, the food we eat, other people, and cosmic radiation. We receive about 1.5 millisieverts of this radiation per year. Regulations for radiation exposure for most people state that you are allowed 1 millisievert per year in addition to the background radiation dose. This is a safe limit since it is not known if there are any ill health effects from radiation doses below 10 millisieverts. To put the 1 millisievert in context, this is equal to approximately 16 chest X-rays or 40 dental X-ray exposures. However, there are medical X-ray exposures that exceed this, such as an abdominal CT scan, which is about 10 millisieverts. So, if you follow the ALARA principle when doing a radiation-based experiment, your dose will be of the order of microsieverts, which is much lower than your daily background radiation dose.